A big part of visual effects work is problem solving when things go wrong, and fracture work is no exception to this. So here we have a piece of geometry from the top of a tower asset, and if we run a quick basic fracture on this, we'll just drop in a scatter node and a Voronoi fracture. Maybe we'll just scatter, a few hundred points and hook this up as we've seen in previous videos. You'll notice that this is giving us a pretty broken result. That does not look clean at all, especially when we compare to the original shape. And it's not just Voronoi fractures that have a problem with this geometry. We haven't talked about booleans yet, which we will get to very shortly, but if we create a quick boolean fracture as well, then we'll see that this result is also broken. If you're wondering why we're using a boolean example here before actually covering boolean fracturing, it's because we're going to use this piece of tower geometry for our boolean fracture setups that are coming up, and I wanted to show you how to fix this geometry before we use it for those boolean examples. So don't feel like you have to recreate this boolean setup while watching this video. Just feel free to digest this information on common problems, and we'll go deeper into boolean stuff in the next video. This is broken in different ways than the Voronoi version is. You can see we have large sections completely missing from the geometry, and some pieces of our cutter geometry existing where they shouldn't be. But in any case, they are both completely wrong. Now, it may be relatively straightforward to set up a basic Voronoi or Boolean fracture, but the algorithms that actually run this fracture process under the hood are pretty complex. So there are lots of little issues that can arise in the geometry that will cause those algorithms to break. Thankfully, most of the problems that arise are caused by the same few issues, and there are some geometry checks that we can use to detect if that's causing the problem. In this particular example, we're running into what's probably the most common cause of fracture problems, and that is when your geometry has little tiny holes in it, and the term we use for this is whether it's watertight or not. Basically, if this object existed in real life and you filled up this mesh with water, would it hold? Are there any little holes in it? They could be pretty obvious holes, or they could be little microscopic, essentially imperceptible holes. And we can detect those holes using a group node. If you drop in a group and connect it to our geometry, you can turn off the base group, which by default will just add all of the mesh points or primitives to the new group. So turn that off, go to Edges and enable that, and turn on Unshared Edges. Now just to keep things clean, let's call this groups up, check unshared, and let's scroll up to the top, and we'll change that group name to be called unshared. So if you middle click and hold on that groups up, you'll see this prim group has 242 prims in it, and you can see those highlighted in the viewport as well. Now this grouping of unshared edges works either on prims or edges, probably points as well. Yep, sure enough it does. And sometimes the primitive view allows you to see exactly where those problem spots are on a complex model. And the edges are less obvious in the context of a complicated model, but that will show you more precisely exactly which edges are the ones that are not sealed in the mesh. So we can see that all of these window cutout areas are problematic. If we switch over to our point selection and perhaps grab one of these points here and then select the transform tool, if you just move that point to the side, you can see that sure enough, although it looked like a sealed mesh surface, there is a disconnect between those edges, and that is causing problems with the fracture. Thankfully, this is pretty easy to fix in this case. If you just drop in a fuse SOP, this will fuse together points that are within a given distance tolerance. And when Houdini fuses these points together, it also knows to fuse together those edges that are between those points. So now, if we use our fused geometry for that Voronoi fracture, and before that, actually, let's check the unshared group. You can see that with that fuse in there, this group is no longer returning any unshared edges, and we can give that fracture a try. And sure enough, we now have some nice clean geometry, and if we test that with an exploded view as well, that geometry looks exactly like we expect it to. Now, if you look at our fused geometry, you'll notice that it still has a whole bunch of edges that have multiple sides to them. I know in some areas of VFX we try to stick with triangles and quads, but the Voronoi and Boolean fracture processes actually do a pretty good job of handling all of these faces that have more sides than that. Of course, if you get desperate when debugging a fracture problem, you could always try using the divide node with maximum edges set to 3 or 4, but I would try all of our other more common problem fixers first. Now, although both Boolean and Voronoi fractures can handle these multi-sided faces pretty well, what works with one fracture type might not work with the other. So let's test it out and connect our fused geometry to our Boolean fracture and run that fracture. And sure enough, this is a very broken result. Now, this broken fracture is due to bad normals. That's not visually obvious from looking at the geometry. I know that's causing the problem because I'm familiar with this piece of geo, but that's another thing that we can check fairly quickly in the viewport as well. To check those normals, I would turn on primitive normals here. I generally don't check this with point normals. And those might be very difficult to see in your shot depending on the scale of your scene. You can probably barely see these little dots at the middle of some of those prims. And part of the reason that we only see those little dots is because those normals are pointing inside the geometry. You can see them a little bit more inside here, but they're also pretty tiny at this scale. So if you hit D to bring up your display options, you can select guides and then increase the scale normal here to something that you can see more easily at your scene scale. So with those scaled up normals, we can clearly see that they're pointing inside the geometry, and we want those to point outwards. We can flip those normals using a reverse node. Now if you display that reverse node, you'll see that all of the normals are now pointing in the correct direction, although they're behaving a little bit strangely, and it makes it look like the normals are broken since we see all these kind of weird shading things happening as we tumble around the viewport. Now oftentimes when you reverse normals like this, they do display funny, and you need to drop in a new normal node in order to fix those. So if you drop in that normal node and display it, then you'll see that our shading is nice and consistent and we don't see all that weirdness as we tumble around it. Now in this case, the Voronoi version worked without that normals fix, but it's still good practice to double check your normals when you're having problems with Voronoi fractures as well. You want your input geometry to be as clean as possible to reduce chances of it bugging out and breaking on you. I've also run into some problem cases where the normals were inconsistent on the geometry. For example, maybe this face would be facing outward and this face would be facing inward. And this doesn't happen as often, but if you have issues like that, one potential way to fix those is with the clean SOP. Now you have to be careful with the clean SOP because this remove degenerate primitives option will delete small faces from your mesh. And I've found that it's overly aggressive with deleting those, and it will sometimes remove faces that are actually totally fine and that you want in your geom. So let's disable that and turn on this orient polygons option. That orient poly option will, as it sounds, figure out which polygons have that the flip-flop direction, and it'll make sure that all the connected polys all point the same way. Like I said, I've not had to use that one often, but it's still a good one to know. The last potential problem I'd like to talk about in this video is an issue when you have extremely large objects or objects sitting at extreme values in world space. You can see that this piece of geometry is at 3,000 units in Y, which is quite a bit, but this was actually originally at 30,000 units in Y. I've scaled it down to 10% of its original size, when I made this cache, that is. And once you start going out to those extreme values, some really weird things can happen. Fracture processes might break, you might run into some rendering issues. There are lots of weird things that can occur. And it's actually not uncommon to get assets at those extreme values of space when working on film projects, because you might have massive environments modeled and action can take place at several different areas of a really massive environment asset. Now, floating point errors are a little bit weird to describe or even to understand exactly what's happening internally in some cases, but the general idea is that in the real world, you have an infinite amount of detail for the positions of things around you. Whereas in a computer, we're kind of restricted to certain numbers of digits or amounts of data that we can store. So there's always a little bit of rounding and approximation that happens when you're working in a computer. This is not just specific to Houdini. You'll have these floating point errors occur in various areas when working in a computer. So if you run into instances where you have things at those extreme scales and these other types of fixes are not doing the trick, then you can feel free to just use a transform node, and you can leave the pivot at the origin and you can just scale it down any amount that you want. I typically go in increments of 10. You can even go down to a multiplier of 0.01 if you need to. And it can also be helpful to physically move an object to the origin as well. In this particular case, I'm going to connect this transform node, and I'll set that scale back to 0.1. And for this translate value, we're going to use the opposite of its center value. So the center of this tower geometry is at, well, let's see, if we turn off that scale, let's leave this back at 1 for now. The center of this is at minus 236 and 3,000 something and 0 and z. And we have this super useful centroid expression that you'll be using a lot throughout the class. And it's this function called centroid that you can type into any parameter, and we need to tell it what we're looking up the centroid of. In this case, I'll just put a 0, which means input number 0 for the current node. And then in the help here, it says you can specify d underscore x, y, or z. So I'll put in d underscore x. And because we want to invert that centroid, we'll just put a minus in front of that centroid there. And we'll copy that. And we'll paste that into y and change dx to dy. And paste it into z and change dx to dz. Just to keep things clean, we'll say move to origin. And if you middle click on that translate, you can see the values that it's using, which is the negative inverse of the center value of our incoming geometry. And sure enough, if we zoom in on our geo, you can see this is placed down at the origin. Now, if you want this to sit more nicely right at y equals 0, instead of having that be right in the middle of it, we can add half of the object's height to this translate here. So we'll say plus 0.5 times, and we'll use this bbox function to check input 0 and look up d underscore y size. So you can see that brings it up to half its height higher in Y, sitting nicely at 0. Now, because our transform order is defaulted to scale, rotate, translate, if you scale this, you'll see this flying through space because it's scaling the object and then applying this this transform on it. But if we flip the order here to do the translate first, and then the scale, and then the rotation, you'll see that it sits correctly right at the origin, and we can scale it up and down as much as we want.